Today we will learn about optimization using AspenPlus. So let's jump into the simulation. So first we will input our components CO2 and water, and our method will be Peng-Robinson method. Okay, so we got no error. Then we will jump to the simulation part. We will make our flow sheet. So our stream contains CO2 and water. So we have to remove the water. For that we will cool down the stream. So we are using a heater, and then we will separate the water from it, and then we will compress it using multi-stage compressor. Okay, so I will finish the input and the flow sheet of this process. So our stream of CO2 is coming at 250 degrees Celsius at 1 bar pressure, and the mass is 1000 kg per hour. So the mole fraction of the stream we will take as 0.85 and H2 is 0.15. Okay, and then next we will cool down this stream to 32 degrees Celsius, and there is no change in the pressure. So next we will separate it based on the adiabatic condition. So we will put the duty as 0, and there is no change in the pressure. Okay, so the next is compressor. Compressor is a 3-stage compressor with an intercooler. Okay, and then it's isentropic model we are using, and there is a fixed discharge condition. So during the compression what happens, there is always a water condensation, and that we can show by the stream S6 and S7. Okay, so for that, so these streams are water streams. So what happens after that, we will specify the outlet of the compressor. Okay, so what we will specify is the discharge pressure of each stage. So values I will put it as 2 bar discharge in the first stage, and 8 bar pressure in the second stage, and outlet is the 18 bar pressure. So efficiencies we can give it, I have taken this from the literature, so I take it as 85%. Second stage is also 85%, third stage is also 85%. We can give the mechanical efficiency. Okay, now the cooler is that we are cooling the our stream, okay, while after each stage. So the cooler outlet temperature we will specify here. Okay, we have given it as 32 degrees Celsius. 32 degrees Celsius, and the last stage is we take it duty as 0. Okay, so whatever the stream temperatures there is, so we are not cooling it. Okay, so this is our specification. So now we will run the flow sheet, and we will see what happens. So how much is the separation of water? So the water is separated out. So this one is 51.4 kg is separated out of 67.37. So the mole fraction, okay, 99% is in the liquid form. Okay, so now the next part is we will see the what is the power consumption. So power consumption is basically 63.560249. Okay, here this is kilowatt. This is our power consumption by the multi-stage compressor. So now we will attach a work stream, 3 work stream for each stages, and then we will mix them. Again we will run it. Okay, so your flow sheet is not complete, so there is something left. Okay, so one we have to specify which stream is for which stage. So these are the work stream that we have just attached. Okay, now we will run. The result is same, 63.56 is the kilowatt is the energy requirement to compress it to 18 bar pressure. Okay, so each stage what we have given, so each stage is, first stage is 2 bar and the second stage is 8 bar and third stage is 18 bar pressure. Okay, now we will use the optimization. So we can see that our requirement of this power is less. Okay, we will optimize this. So what is our, so W is our variable, so variable is our power. So which one is that? So this is S11. S11 is our total power, it should be minimized. So W. Okay, and what we are doing, so what are the variables that we can manipulate or vary to change this power consumption? So that is our so pressure at the outlet. Okay, see these two, 8 and 18 at each stages, it should be like that, it should change such that the optimum condition our power consumption should be less. So what we will do is we will vary these. So compressor, so in this ID1 window we will put first, so it shows the first stage, it will vary from 2 to 18 new. The second, for the second stage it will also change it from 2 to 18. Okay, so these are our, this is our whole definition of optimization in the AspenPlus. So we will run it and we will see what will be the results. Okay, so our run is successful and we got the results, and then we will check the results. Okay, now what happened is 62.8423 kilowatt. So we are getting a requirement of less power for the compressor. Okay, and each stage, the first stage is at 2.55, okay, it's 2.55 bar, second stage is at 6.94 bar, and third stage is at 18 bar. Okay, now the other thing is we can also put the constraint. So constraint is that suppose we want that okay, any constraint is that what we can see that we see block variable, so compressor. So first, okay, the first stage we talk about the first stage, and then it should not be greater than or equal to 1.5. okay, it should, so this is our constraint. Suppose we have a constraint that it should not be one greater than or equal to 1.5, the first stage pressure. So what we will do is P1, and the tolerance should be 0.001. Then we have to add this constraint in our optimization, and now run again. Now if we look at the results, see there is a change in the power, 62.8422767 kilowatt, and okay, so C1 is inactive, the constraint is not taking any effect. Okay, why it is not taking any effect? Oh, it should be less than or equal to, okay, it should not be. Okay, now it is showing some errors. Okay, so it is saying there is no feasible point, so the optimizer is not coming to any feasible point. So what we need to do is, so what if we change it to 2, and we will say that it should be less than or equal to 6 or equal to 6. This is our constraint. Now we will see that if the optimizer will find a feasible point or not. Okay, there is some point. Okay, so now we will see that okay, it has found 62.919597 kilowatt. Okay, so the second stage is at 6 converged. Okay, the constraint is also converged. So this problem is constraint optimization. But I think it is less than, if we remove this, what happens to this kilowatt power consumption. So let's see, 62.84. okay, if you remove the constraint, now this is an unconstrained optimization problem, because we have removed this constraint. So the result is 62.84227. And if we include this constraint, then what happens is, okay, 62.91. So our power requirement increases, okay, from 62.8 to 62.9. Okay, this way we can make it constrained or unconstrained problem. So hopefully you understood how to use the AspenPlus for optimization and use the constraint for constraint optimization problem. So other thing which we can see is what are the methods used during the optimization. No, so conduct out the optimization. So methods, if we see direct, secant, default methods, okay. Default, so for optimization we are using SQP method. So if you want to change it to complex or BBYQA method, so let's see if changes something. So if we change this, our previously our result is 62.919597 kilowatt. Let's see. Okay, yes, there is a change because we changed the method. So our default method is now complex and the result is 62.85 kilowatt. Okay, now you see, now we will use the third our method for optimization. Okay, this also changes. So we can use any one from the three optimizer methods, and the default is SQP. So it's depend upon how complex is your problem is, and we will get the results. Okay, yes. So hope you understood the concept of optimization using AspenPlus and using various methods also. We can change the methods. Okay, this is very powerful tool to optimize your problem, chemical problem. Thank you. Take care.